Hi, everyone. I'm Arjun Narayan, your host. With me, I have Josh. We're going to give folks a few more minutes to connect before we get started. Thank you very much for your patience. We can see folks sort of joining in, so I'm just going to keep going. Josh, can you do a quick mic check? Can you say something?
Yeah, hello.
All right.
Glad
And
to
we've
be
got
here.
the slide share going. All right. I'm getting some messages that we're sounding good. So as soon as ready to go. Just, I think we'll kick it off in a couple minutes after. So that's just one more minute. All right, I think we're going to get going. Thanks everyone for joining me. And Josh, I'm Arjun Narayan. I am a co-founder of Materialize. With me, I have Josh Orenberg. Josh is a member of our field team, um, and we'll be doing the hands-on demo components of today's presentation. So today I'm going to walk you through a little bit about, hands-on with Materialize and sort of where you would use it and how it sort of compares to a typical sort of data architecture setup that involves, an OLTP database, in our case, Postgres, but really sort of could generalize to many others, where you have a lot of read replicas and you're handling some pretty data intensive queries, right? So a quick sort of outline of what we're going to talk about. So I'm going to cover sort of what current architectures look like, typical architectures that you might have in your organization, what an architecture with Materialize would look like, and then we've come up with FreshMart, which is a example scenario that sort of Josh will get into that, but sort of mimics what we see in production. That a lot of people who use Materialize, what their setup looks like. Excuse me. And then I'll talk a little bit about benchmarking because it's one of my passions. I've been working on databases for a while and I really care about benchmarks. And so, talking about how you could actually measure this faithfully. Then we'll jump into a live demo of the benchmarks, which is a different setup. We can really sort of see Materialize being pushed to higher load levels. We have a whole bunch of reproduction steps and all that up on GitHub, and we'll walk you through that so you can use that yourself. We'll have plenty of time for questions, and I really encourage people to pop questions in the chat. I'm going to be monitoring it, so I don't hold back. I will definitely address all questions at the end, but if something's a relevant question to a slide, I'm happy to sort of do it interactively as well. So don't hold yourself back. With that, let's go. So here's a sort of prompting sort of opening question, right? So let's say you have some data intensive queries that need to be fresh and correct. What can you do? And for this, we're going to have to do some defining, right? Like what do we mean by data intensive queries? I just want to keep it very simple and intuitive, right? So, we've got all sorts of shapes and sizes of possible queries. You can have your point lookups, you can have simple reads, simple writes, but think of something more complex, something that sort of looks through a whole bunch of data, like some large aggregation, large joins, sort of multi-way joins, just something that sort of inherently involves sort of scraping over a whole bunch of data, right? So that's what I mean by data intensive queries. If you've written queries that run against the data warehouse, I'm talking that kind of query, right? When I say fresh, this is sort of deliberately not, I'm not saying low latency, right? Because there's sort of two concerns that we have. Latency is sort of the time between when you ask the question and when you get the result, right? So you could have, you ask a query, you get a response in 20 milliseconds, but that answer is based off of some data that is 2 hours old. That would not be fresh, right? That would be stale but low latency. Similarly, you can have sort of fairly high latency but fresh. And that's sort of typically what you would see when running data intensive queries directly on your OLTP database, right? So it could take 20 seconds to answer your query, but that data is, as of that exact same data when that query was started. Now it's hard to have latency that's lower than your freshness, right? So like the latency is sort of a hard minimum bound in your freshness, but you definitely can be very, very not fresh but low latency. And so that's why I want to sort of keep these concepts separate in your head. And of course, really, we really care about correct answers, right? So we're not talking about eventual consistency in, inconsistent caches, things like that. You need some fresh um, data intensive queries to run. You need the answers to be correct. What can you do, right? So let's start with a simple data architecture, right? Like when the first thing everybody starts off, right? They have an OLTP database, right? You have a startup day one, you're provisioning an OLTP database, right? All the data sort of begins there. Over here, we're going to use Postgres. There's many OLTP databases that you could use, a Oracle, a Cockroach DB, a Yugabyte, a MySQL. Just to simplify, we're just going to, think of it as Postgres. You could have other sources, right? You could have event data coming from segment webhooks. You could have data coming from Kafka topics, all sorts of things. But, let's just say you have a Postgres database, right? You want to ask some queries off of it. You can ask a lot of simple queries, but it's challenging to ask complex queries. Now you still can do it, right? You can execute very complex SQL. It's just not going to be very fast, right? And it's going to hog a lot of your Postgres resources. So what do you do, especially if you're worried about, disrupting the production traffic or things like that? Well, a great thing you could do is just like stick a read replica there, right? So at least you've achieved some level of resource isolation, right? So when send some five-way join query that sort of does full table scans, at least it's not going to affect the primary replica. It's only going to hit your read replica, right? It's still not great. It's still not, it's still not going to respond very quickly. And as we'll look in the demo portion, when you sort of put Aurora Postgres under this sort of strain, 10-second queries, not atypical. Now, of course, you can stick a cache on it, but now you have to worry about, is that cache consistent, right? And why is this? Why fundamentally, what's going on here, right? And the answer is very simple, that databases, OLTP databases, have one real workhorse for speeding up queries, and that is the index, right? And we're all familiar with database indexes. You can create a lot of them. You can create, all the secondary indexes that you want. But indexes, one way to think about it, they really only allow you to index a set of columns. And what that means is there's one particular pattern of query that gets sped up by the creation of an index. And that is a query that looks like select blah from a single table, right? Where column X equals blah, column Y equals blah, column Z equals blah. And you could have lots of different query in columns that are indexed jointly, as long as they all come from a single table, right? And if your query doesn't sort of fit that shape, like the index is sort of limited in its ability to help you get a fast answer, right? But what if you could index an arbitrary query? And that's sort of if there's one thing I want you to take away from this, is that that's really, what a materialized view is. It's a generalization of a database index to a broader, richer set of queries, right? So like, imagine you could create an index for a query that looks like this, right? This is a three-table join, right? It has a group by aggregation over there. You got two aggregations, sorry, two counts, a group by user ID. And what if you could build an index that kept the full result of this query up to date? And that's really what a materialized view is. And of course, the hard part of view materialization is keeping this index up to date without just sort of throwing everything out and recomputing everything from scratch every time there's an insert to one of those three base tables, right? Like a lot of OLTP databases have materialized views that have to be manually refreshed. What that basically is, it's sort of like saving the answer, storing the answer to the query, like in a cache. And anytime the underlying data changes, you got to rerun that whole query. But that's not really the answer that we want. We want a materialized view that is efficiently and easily maintainable incrementally, right? Um, so that's what we want. But what other tools do we have? What do we have in our data stack that can do data intensive stuff, right? So another great workhorse tool we have is a data warehouse, right? These OLAP engines, these analytical processing engines, are really good at processing large, fully parallelized joins, aggregations, things like that, with one catch. As long as the data is fixed, right? So if you batch load all your data into a data warehouse, that data warehouse is going to be really good on that batch of data. So the catch is, right, you sort of two things. You got, fresh data on the left over here, your OLTP systems, which are good and efficient at keeping that data fresh, but not really good at processing those data intensive queries. And then you've got this other workhorse that's really good at processing data intensive queries, but the data is really hard to keep fresh, right? So that's really where Materialize fits in. When you have a requirement for both data intensive queries that need to be fresh, use it in the place of a read replica, right? Where and it fits right there as far as the upstream Postgres is concerned. It looks like a read replica. It takes a replication slot just as a regular Postgres read replica would. It also connects to MySQL in the exact same way. It connects to Kafka. You can use Debezium, whatever you want to use to get those changes in that works in your data architecture. Same thing. That's how Materialize is going to fit in. And then to those data consumers, they query it just like Postgres, right? So it's really a read replica for scaling reads for data intensive workloads, right? So what else could you do, right? Like you have other tools available. One thing you could do is build some microservices, right? So you could take these changes using a change data capture service like Debezium. You could put all those data into Kafka topics. You can then use some Flink jobs to process that. And then you could stick the results in a Redis cache. And then your data consumers could read directly from that Redis cache, right? And of course, a lot of you probably have data architectures that already include this component. The real challenge here is you're on the hook for all of the deployment and the scalability and the sort of schema evolution and the maintainability of the system. And you are on the hook for correctness. And this is the hard part of this system, right? It's all of the challenges are around what to do when this is changing and you need to keep all the answers correct. So Materialize is an operational data store that fits right here, allowing you to integrate this data, and it allows you to do low latency, fresh results that are correct. So how does it work? How does this happen? Right. So Materialize under the hood has a scale out storage layer that where all of the data that you ingest from your OLTP sources or your streaming sources gets stored cheaply and efficiently on S3. Give me 1 second. You can spin up these compute clusters that give you isolated compute resources to host these materialized views that are incrementally maintained over time. Under the hood, there's continuous transformations powered by stream processing going on. But the nice thing is that from the user's perspective, they interact with it just as they interact with a SQL database, right? So they could write SQL queries, or they could have Materialize push this out to a system like Kafka. All right, so let's take a look at what that's a lot of talking. I kind of want to throw it to Josh to sort of give you a hands-on overview of what Materialize looks like. So Josh, take it away.
Great. Thanks so much, Arjun. So by way of introduction, I'm Josh. I have been with the Materialize field team for about 2 years. And before that, I was Materialize's first customer. So these problems are very near and dear to my heart. And I've been in the position of trying to solve them before. And so glad to be able to show you how we do that at Materialize. So the first thing, and I'm going to demo 2 things today, right? First, we're going to do sort of a real world example of a Materialize use case and what that might look like through a fictional retailer called Freshmart. And then after that, Arjun and I are going to take a look at some benchmarking. But first, let's talk about Freshmart. So Freshmart, for this demo, is an online retailer, and they're selling produce and grocery items. Their primary database is Aurora Postgres, and they've been using it for some years. It's been very successful. They have gotten consistency, correctness, high availability, and you can see here's sort of what their schema looks like: products, categories, suppliers, sales, inventory, and promotions, right? This is kind of a basic online retailer. And but they've recently been faced with a new challenge, and that is that the business has decided that they want to start offering dynamic pricing. And by that, they mean that the price of any of their items is going to fluctuate based on the available inventory, snap promotions, popularity, and maybe some other factors. So this is a new challenge for their data architecture, and they've outlined several requirements for the solution. So the first important requirement is correctness, right? We need to always see the most up-to-date price for an item. Eventually consistent is not an option here. The second requirement is that it needs to be maintainable, keeping the team agile, right? And it needs to be easy to bring to production and straightforward to modify. And then finally, it needs to be scalable and cost effective. Okay, so with those requirements in mind, let's look at how we can achieve this. All of the data necessary to compute the item dynamic price, it already exists within our Postgres database. And even better, the logic for computing the price can be expressed as a SQL query. And this is what that query looks like. You can see that this very much fits our definition of a data-intensive query, right? We have subqueries here. We have some window functions, lateral joins. So, you know, it gets a little gnarly in here. It's the sort of thing that you need a real database for. Because this can all be computed in a Postgres query, the first solution that Freshmart came to was a read replica. So in fact, they looked at this and said, well, this is way too complex to run directly on our production database. Let's spin up an extra large instance in AWS and try it that way. And this way, the workload will be isolated and we'll have resources to run the query. So let's take a look at what that looks like. Here is that Postgres instance, and we're just going to run this select from dynamic pricing. Dynamic pricing is this view that we just saw, right? This is the dynamic pricing view. Let's go ahead and run that against product ID 1. And you'll see part of the challenge of this demo is finding good things to talk about while Postgres is still doing its thing here. But behind the scenes, okay, so here we have an answer, and you see it's taken about 13 seconds just to generate the price for one item, right? This is less than ideal, obviously. It's a bit slow for a production system, but then when Freshmart really starts to think about it, they say, well, hang on a second, this is just one item. We're going to have multiple concurrent requests for pricing running all day long. So we're actually going to use a tool like dbbench. We'll use dbbench to spin up 10 concurrent connections, and we're going to perform that same query for 60 seconds. And you'll see that the performance rapidly deteriorates. Now, while this is running, I want to show you, we're not cheating here, right? We have fully indexed this query. If you look, we have primary and secondary indexes here. As I mentioned, we're running on an extra large read replica. So in theory, this should be some pretty powerful compute. But the thing is, as you know, even with a read replica, it's still a transactional database. The data is still arranged to optimize for fast single transaction operations. And here we're scanning over a lot of data. We're doing, what would probably be classified as more of an analytic type of workload, but we need to do it obviously fresh and in real time. So, we're starting to see some answers here. Our latency is starting to look like 30%, right? With P99 being up, 34 seconds, 33 seconds. Okay, we've got a problem here, right? In this entire time, we were only able to complete 21 transactions, and our average latency of 31 seconds. This is not going to cut it for a production system that's doing the pricing for the store. Okay, so back to the drawing board. There are a few other things that their engineering team has looked into. The first of which is a cache, right? This is a very common solution to data-intensive queries on a read replica. In fact, it's so common that when they went to spin up their AWS instance, it actually asked them, hey, do you want to create an Elastic Cache instance to serve this request, to serve these requests? And, in some cases, this might be feasible, but in this case, as we mentioned, like correctness is very important. They need the absolute most recent price. And the thing about a cache is that cache invalidation is a very hard problem, and the cache can be stale. So it doesn't give us the correctness guarantee we need. And then the third thing, as they started to investigate, they said, well, maybe we're looking at a bespoke service here. But when they started to look at it, I mean, that's a separate development team. Requires scaling up a whole development process, and also moving all of this pricing logic from outside of the database into an external service. So a very heavy lift. But that's when they discovered Materialize. So Freshmart was intrigued by the fact that Materialize acts almost like a smarter read replica, right? Giving them the missing piece of their data architecture here, which is an always up-to-date materialized view. Okay. And when we started to look into it, Materialize can seamlessly integrate with Aurora Postgres, consuming the changes directly using logical replication, right? Aurora Materialize will just appear like any other read replica, right? So they found that Materialize offers strong consistency, respecting the upstream transaction boundaries from Postgres. And so this is crucial because it means that the dynamic pricing logic will always have access to the most accurate and up-to-date data. And the most compelling feature, however, with Materialize is that it moves the work from the write path to the read path, meaning that instead
From
of...
the read path to the write path.
What's that?
From the read path to the write path, I think you
Yes,
said
exactly.
backwards.
Yeah. It moves the work from the read path to the write path, allowing users to index their views. This means that instead of computing the price of a product each time a query is made, Materialize can pre-compute and maintain the results of the complex queries as the underlying data changes. And this shift will drastically reduce the load on the read path, making queries nearly instantaneous and eliminating the performance bottlenecks that they were facing. So let's take a look. This is Materialize, right? When you open it up, you get a console. Actually, it's a Postgres console, and in fact, Materialize is Postgres compatible. Let's look at how they stood this query up in Materialize, right? The first thing that they did is, and as you can see here, this is the data view. And you can see that it's organized much like a database. So you have schemas and databases similar to how you do in Postgres. And here, this create view statement is actually identical to the one that we had in Postgres. So the very same query that we already looked at here. The only thing is that instead of the indexes, the Postgres indexes that we saw before, we have this, which is a Materialize index. And we're indexing the entire view. So by running this behind the scenes, Materialize is spinning up a data stream to keep these results up to date. Now let's go ahead and test this out, right? We are going to run, let's see, let me clear the screen here. We will run on the public schema using the pricing cluster. And this is the exact same query that we ran before at the very beginning, and it took 12 seconds. There we go. You see 36 milliseconds. And just to refresh our memory, we can see it's the very same answer, 804.32, right? So we can see we've got a correct answer here. This is very exciting, meets the first requirement. However, we've done some work up front, right? We need to make sure that Materialize can respond to changes. And so let's see what happens when let's actually make a change upstream in the Postgres database. So here we're going to now run this query to update a promotion. So we're going to run a special promotion for our product ID number 1, update that in the upstream database. That change for the promotion flows through immediately to Postgres or to Materialize. And now when we run it, we see an updated price of $7.72. And in fact, if we run again here, we'll see in about 12 seconds, we'll get the same answer here as well. But while we're doing that, there's one more thing that we want to check here, and that is, okay, it's all well and good when we know exactly the query that we want to run ahead of time up, and as we see, we get the same answer in Postgres. So it's all well and good when we know the entire query that we want to run ahead of time, but maybe that's not always the case, right? Sometimes there's things that you only know at query time. And the exciting thing with Materialize is that we actually have the ability to run ad hoc queries using these same indexes. So for this example, we want to institute a membership discount, but we'll only have the details for the membership discount at query time. But we're actually going to be accessing the same pre-indexed dynamic pricing model that we looked at before. But if we run this, you'll see, again, 200 milliseconds for this ad hoc query because of the pre-work that's been done upstream in the dynamic pricing view. So that's the end of this scenario. I hope it's shown how Materialize can be used to dramatically speed up data-intensive queries on a Postgres database. Thank you.
Thanks so much, Josh. Thanks for that demo. Back to sort of talking about what we saw there. One of the things that Josh mentioned was that these indexes can be used even for queries that don't fit that precise Materialize view. That's very important, right? Like that gives you the ability to handle flexible query patterns, You sort of think of it as like you have this slider, you can fully materialize, you can sort of partially materialize, whereas with a more traditional OLTP index, you can only do that index on that one table set of columns. But over here, you could actually dynamically choose how much materialization you want. And it speeds up queries again. And again, it's not magic beans. There's no sort of free lunch here. If you only halfway materialize, you're still going to have to do that other half at query time. So there's a trade-off here, but you get to choose the trade-off based off of how dynamic your query patterns are. And we have customers who have, more dynamic queries, and they have customers who have like, I have this one fraud detection query, and that same query needs to be very, very fast. Yeah, so it really depends on your workload. So why choose a system like Materialize, right? Like, and we have three product principles. It really just comes down to the fact that we really really care about these, and the biggest one is correctness, right? So trust, scale, and ease. Trust means that you can trust that the answer you get out of Materialize is very fresh and correct. So the isolation guarantee we offer is strict serializability, which basically means at the time at which you press the enter button on your query, or when you issued the query, at that time, all the data that was available up to that is incorporated in the answer, right? So even though you're getting a very low latency answer, it's also very fresh, right? So
Hey, Arjun,
from the
we're not seeing your slide at the
yes.
moment.
Oh, did I not share my screen correctly? Let me try that one again. Thank you
Sorry
for
to
pointing that
interrupt.
out, Josh. I appreciate that. Do you see it now? You see a screen share?
Yes, now we can.
Perfect. Yeah. So our three product principles. Thanks so much, Josh. Trust, scale, and ease. The second one is it's scaled. It's built on a scalable stream processor. This way you can take advantage of lots of cores. You can take advantage of multiple nodes. All of it is sort of nicely abstracted away. So it's still the same SQL terminal, which brings us to ease, which is you just write SQL, right? So that was a pretty data intensive query that Josh showed you. We have customers using, multiple hundred line SQL queries, or, complex logic, but like that would get way more complex if it was, thousands of lines of Java code. So let's sort of take that simple demo and sort of expand that into something that's like far more firepower in terms of what is being thrown at Materialize. When we're talking about benchmarks, right? So for Materialize compared to a Postgres read replica, we built this benchmark suite, which is available on GitHub. I'll post the link in the chat. And the short answer is, Materialize is a lot more handles a lot more throughput, much lower latency for your answers. This also ends up being a lot cheaper because you can end up replacing a lot of read replicas with a fairly small Materialize instance, right? So when building benchmarks, I've done a lot of benchmarking in my life. It's pretty challenging to sort of do faithfully. It's very easy to have a hacky benchmark that says my system good, your system bad, right? But like to be faithful to these systems, there's a wide variety of benchmarks, right? There's for OLTP systems, there's TPC-C, TPC-E, which are 30-year-old and 20-year-old benchmarks to really stress test OLTP databases. For data-intensive queries on batch data, there's TPCH, which is a list of 22 very complex queries, TPCDS, which is about 100 of those similar queries. And you can think of these as queries that you would, like an analyst might run, like a business analyst saying, I want to compare this quarter's sales versus, last year's same quarter sales across my sales regions. I got to join all this data, but it's not the kind of query that you need to keep fresh, right? So it's like not correct to say we can just take that query and start changing that underlying data, because no rational individual would care about making sure that their once a quarter sales report processed in sub-second latencies, right? And by the way, these benchmarks are very good at the core workhorse workloads for the systems, right? So just as if you run TPCC on Snowflake, you get a lousy answer, or you run TPCH on Aurora, you're going to get a lousy answer. These benchmarks are designed to really stress in an honest evaluation of those systems' strengths, OLTP and OLAP. You can't really just smush them together. There was one academic attempt called CH benchmark, but again, runs into these flaws that it's not really the correct intent that these are the queries that one would actually want to keep fresh. So data intensive workloads surely just don't have a benchmark suite that really tests freshness. So we designed one, right? And this we've shared all of this publicly. You can reproduce this from our GitHub. And basically how the setup goes is there is a primary Postgres database where writes are happening. We're testing two different read replicas, one Postgres and one Materialize. Both of those are connected via logical replication. All the writes are processed on the primary, and the data-intensive read queries are issued to the read replica. And we sort of measure QPS and latency for our read replica, assuming that it's going to be fresh. You could also stick a data warehouse, but then you'd sort of need to have an end-to-end freshness metric that you test there too. We assume that you're not going to do that, right? So with that, I'm going to throw it back to you, Josh, to give us a quick benchmarking demo.
Great, thanks, Arjun. Let me share my screen. All right, so as you mentioned, Arjun, we've been developing our own benchmark for data-intensive queries, like you might find on a read replica. And so what's in this benchmark? Well, the data layout looks a lot like a trading system. So we have tables for customers, accounts, securities, trades, orders, and market data. And there are 16 views that are used in the benchmark. And so, as Arjun mentioned, what's going to happen is the benchmarking tool is going to spin up an instant. It's going to spin up, and it's going to simultaneously write data into the main Postgres instance, and then it is going to read from either the Postgres read replica or from Materialize as a way to benchmark using these 16 queries. And by the way, if you'd like to read further into the methodology or exactly what's contained in these benchmarks or the code for the benchmarking tool, it's all available on GitHub, and we will put a link into the chat here if anybody would like to check out that code. Here's the 16 queries. You'll notice they kind of get increasingly complex. Starts with, things like an aggregation and a multi-way join and a group by. Here we've got subqueries, complex joins, having clauses, various aggregations. You see window functions in here. And as we go up, we'll see, and by the way, we're doing things like, market overview, recent large trades, customer order book, sector performance. So these are the types of things that are aggregating data. The sorts of things that back in the day it might have been in an end of day report or something like that. But today, I mean, we see this stuff all over the place. Data apps, people need real-time access to this stuff. Sector performance, high value customers. And you can see they're getting increasingly complex, right? As we get up to the 16th one here, we see we've got quite a bit going on with these queries. So let's get to the meat here. We're going to run this. And by the way, we can choose how many concurrent instances and how long. Just for simplicity, we're going to run a single concurrent instance across a 10-second period. So right now, you can see the upstream, the one that I've just kicked off this is our Postgres main instance, and this is our read replica. And so you can see in that test, we were able to complete 5 transactions, and we had a maximum latency of about 8.5 seconds, a minimum latency of 370 milliseconds. And now let's run this same test. The only change that I'm making here is our reader instance is now going to be Postgres. And basically, if you remember in the first demo how we had set up all of the views, right? Those 16 test views have been set up as indexes in Materialize. So similar to how we did before on the Postgres side, we had column-based indexes. On the Materialize side, we have indexes on the views. So let's kick the same test off here in Materialize, and we'll see the difference that having Materialize able to incrementally maintain those indexes on the views can actually make. So you can see, rather than 5, we've managed to do 31 transactions in that same amount of time. And you can see our max latency here is only about a tenth, and a minimum latency of only 26 milliseconds. So a real difference here, even against this difficult benchmark. And so that's it. Thank you very much.
Thank you so much, Josh. Yeah, and so let's we've got some good questions here. I want to sort of make sure we get to them. So one great question, sort of how do customers manage migrations and so creation and maintenance of views on top of raw data? Is it more sort of like a warehouse model where people use DBT, or closer to like production code where migrations are maintained by the team that manages the right database? Josh, you're an excellent one to answer this one.
Yeah. So I would say that the nice thing about Materialize is the user interface is that of a database. So lots of times we have seen, if you have data engineers, they're often the ones that are working on this. We have seen analytics team members. We've also seen DBAs. Folks with a strong skill set in SQL, typically, maintaining the views. As far as the infrastructure side of it, we do support Terraform. So sometimes you'll see an infrastructure team managing the Materialize clusters and so forth in Terraform, but it's pretty flexible. We do support DBT so that you can treat your queries as code, and when you use DBT, it's for those that are familiar with the DBT tool, it's often used in the analytical space to run like batch streams and things like that. But in the case of Materialize, rather than using DBT every time you want to update the data, you run DBT once and it deploys to Materialize, and then you're done. So DBT becomes more of a deployment tool in our case. I hope that answered
Yeah,
your question.
and in my experience as well, customers really like using DBT because it's just like a great ergonomic way to manage your logic.
Yeah.
But yeah, the again the longer answer is that we have people who come in with lots of different data architectures, and they usually have an opinion about what they want to use. And the great thing about sort of being a standard SQL, supporting standard SQL tooling, is most of the things just do end up working and fit exactly your workflow. Another question, can a customer choose the flavor of Postgres used beneath Materialize? I mean, you mean the data coming to Materialize? Aurora, yes. Josh's demo was using Aurora as the source data. Really, the short answer is anything that exposes a Postgres compatible logical replication slot is something Materialize can connect to. Some databases support that out of the box. Aurora, all the ones that are sort of marketed as Postgres typically do. The ones that are marketed as Postgres compatible, like a Cockroach or a Yugabyte, actually have a completely different implementation under the hood. So those don't work out of the box. You need to use additional change data capture to connect to those. But we do have customers doing that as well.
We actually are supporting Yugabyte these days, so that's as of recently, yeah.
But we built
Yeah,
our custom Yugabyte connector,
yeah.
right? Yeah.
But yeah, I think that's a great answer as far as source database. If what you're talking about is like the database that underlies Materialize, like to be clear, like Materialize is a from scratch database, right? So there's no underlying Postgres underneath the product. It is a brand new database that we're offering here. Yeah.
One interesting point that Nate has is that the nice read replica experience really lets you separate concerns, right? From as far as the production database owners are concerned, they open a replication slot and then that's it, right? So it's you get a full decoupling. You also get a decoupling inside Materialize. So we didn't really go into this in this demo. We don't have time to do a full product tour, but Materialize has a notion of clusters, and different clusters are different sets of resources, just like you might think of a Snowflake virtual warehouse, right? So when like team A has their set of clusters, team B can have a different set of clusters. You can use role-based access control if you sort of want team A to build a single data product that can be used by a downstream team B, but otherwise they don't get to sort of use the same resources as team A. And so you have a nice separation of concerns, even inside of Materialize, not just between Materialize and your upstream systems. Another question, you know, Materialize used to be a streaming database. So one of the things we found is a lot of people are allergic to the word streaming, and a large part of the value of Materialize is we encapsulate all the hard work of streaming, and you get the nice database experience, right? So a lot of the point of Materialize is that you don't have to build and maintain all of these complex streaming applications. You're getting all of the benefits, and so it is under the hood a streaming fully scale out stream processor that is doing the materialization, but the sort of look and feel is very much that of a database.
Yeah, and in terms of architectural change, depending on when you looked at us last, right? We've built a whole scalable SaaS solution, right? Since the early days, so now it's both horizontally and vertically scalable. And there's this shared storage layer, which means that if you do have multiple clusters, it's still possible to have all of the resource encapsulation of having multiple clusters, and you can lock down the permissions. So different teams have their own lockdown environments within Materialize, but since they're on top of the same shared storage, provided that you want them to be able to, you can completely join across them, do transactionally safe operations across the data from all the multiple clusters. And so this is a really powerful combination, I think.
Well, thanks everyone. We are at time. You can check out Materialize, materialize.com. You can use it, just sign up right there, get access to Materialize clusters and start playing around with it. If you have any questions, please, contact us. We'd be happy to chat more. If you want to talk about your specific use case, you just generally have more questions. Thanks very much for your time, and hope you enjoy the rest of your day.